Morning dear student. Today I am going to discuss with you normal electrocardiogram. In my previous lecture we discussed what is normal electrocardiogram, what are the different kind of the electrocardiogram leads that is used to record the electrocardiogram, how these leads are placed in the body or the placement of the leads. In today's lecture, we are going to discuss how the electrical activities in the heart occurs and how this electrical activities in the heart is responsible for the generation of the different waves which is recorded during the electrocardiogram. So, learning objective of my lectures is at the end of my lecture you must able to answer the following: sequential electrical activity of the heart, different waves of ECG, you have to define the vectors, and what is cardiac axis. Normal electrocardiogram, it is the record of potential fluctuation during the cardiac cycle. Sequential spread of excitation in the atria, interventricular septum, ventricular wall, and finally repolarization of the myometriums occur. Positive and negative waves are recorded during each cardiac cycle. The waves which are recorded are the P wave, Q wave, R wave, S wave, and the T wave. As we know that SA node is the pacemaker of the heart. It generated the impulses. These impulses start the electrical activities in the heart in the form of the action potential. The action potential formed by the depolarization waves and the repolarization wave. Now, how these depolarization waves and repolarization waves it act? Now, depolarization waves it move toward a positive electrode, gives an upward deflection. If it move away from the electrode, it causes the downward deflection or the negative deflection. If depolarization wave move perpendicular to an electrode, will produce a partly positive and partly negative deflection, that is known as the biphasic wave. While this repolarization process is similar to that of the depolarization, but all the changes occurs in the reverse direction. Like when the wave of repolarization moving toward a positive electrode, it produces a negative deflection. When it moves towards the away from the positive, when it move away, it causes a positive deflection. So it is the just reverse of the depolarization process. A perpendicular wave produces deflection in the biphasic wave. Cardiac vectors. Cardiac vector, we know that during cardiac cycle, current flow in the heart at every time or every instant. The magnitude and direction of potential generated can be represented in the form of arrow, which is called the vector. The arrowhead points toward the direction. The length of arrow is drawn proportional to the voltage of potential. Direction of electrical potential is from base of ventricle toward the apex. Now we see the electrical activity of the heart. How this electrical activity can causes the depolarization and the repolarization of the heart. Now the first electrical activity of the heart is the depolarization of the atria. This depolarization of the atria, it starts from the SA node. As we know, SA node is a pacemaker of the heart. When the SA node it start firing, it causes the depolarization of the atria. The SA node it is present on the upper and the right side of the heart. When it fire, it produces the or it sends impulses first in the atria toward the right atria. When the depolarization waves are formed, so electric current is generated. So electric current is generated and it travels from downward toward the left side. Depolarization wave generate the small vector. As we discussed, the vector it tells the magnitude and direction of potential generated, and it can be represented in the form of the arrow, which is called the vector. We know that SA node, it causes the depolarization first of the right atrium and then to the left atrium. The depolarization wave is in the form of the vector or the electric current or in the form of the vector. Now this wave of depolarization, it moves or it is spread towards the whole of the right atria and then it is spread towards the left atria. We know that there is a syncytium is present between the right atria and the left atria. So the impulses, it moves from the right atria toward the left atrium. So the moment of the vector, it is the downward and toward the left side. All the vectors, these are the summated together. All the small vectors, these are summated together and produce the one single vector. This single vector, it is known as the atrial depolarization vector. This vector represents electromagnetic force which produced in heart when both atria undergo depolarization. So it is a atrial depolarization vector. When the impulses, it reaches toward the junction of the atria and the ventricle, in between the junction of the atria and the ventricle, the fibrous annulus is the present. This fibrous annulus, it is the bed conductor of the heart. Electricity. It is the bed conductor of electricity. So it does not allow impulses to passes through it. Whatever the amount of the impulses, it is coming in contact with the fibrous annulus, it dies out. So only channel of the communication between the atria and the ventricles are the AV node, atrioventricular node. So all the impulses are passes via the atrioventricular node to the ventricles. So first electrical activity is the depolarization of the atria. Atrial depolarization vector is the produced, which is the small vector directed downward and toward the left side, and it is the moderate velocity. It is the small vector because atrial musculatures are very thin. Atria do not have fast conducting system, so it moving with the moderate velocity. Now the second electrical event is stimulation of the atrioventricular node. Current passes very slowly through the AV node. Specialized in low conduction of depolarization. Because in the AV node many small cells are present. These small cells are present in such a way such a way that they does not allow the impulses to passes very fast. In spite of that, these cells they don't have the gap junctions, and gap junctions are very few in the number. When the gap junctions are very few in the number, the wave of depolarization, it travel very slowly because it have to pass and cross each and every cells. That's why the conduction is the less. And also AV node depend on the calcium, as we know that the calcium channels are very slow in it is very slow, so they required more time to conduct the wave of the depolarization. So the AV node specializes in low conduction of depolarization. Because of this, current held in AV node for a while, so that atria complete its contraction and fill the ventricle. So ventricle undergo contraction period. So the vector which is produced due to the depolarization of the AV node is very small. It is very small that the ECG machine cannot pick up the activity of the AV node and show no activity of the heart. So heart is considered as the electrically silent during the second electrical event of the heart. So the stimulation of the AV node show the electrically silent state of the heart. Then we move toward the third activity of the electrical activity of the heart, that is the depolarization of the interventricular septum. Now the impulses, it arises from the SA node, reaches toward the atria, from the atria AV node, and from the AV node these impulses, it reaches toward the interventricular septum, or it enters into the ventricle. In the ventricle, depolarization occur in the three phases. First, depolarization occur in the interventricular septum. Second, depolarization occur in the whole part of the ventricle. Third, depolarization occurs in the basal part of the ventricle. As in the diagram, there is the interventricular septum, Purkinje fibers are there, base of the ventricle, apex of the ventricle. Base of the ventricle, it is present at the upper side, and the apex of the ventricle, it is the downside. Now the third electrical phase of the heart. The interventricular septal branches are stimulated. Now these interventricular septum branches are stimulated mainly by the left ventricular myocardium. In the diagram, I showed the arrow that the left ventricular myocardium, it stimulates the lower part of the interventricular septum. This septum, it is not stimulated by the right ventricular myocardium. So the wave of depolarization, it starts from the left side of the ventricle. Left side of the ventricle, so lower, from the low side, from the lower interventricular septum, and from the left side. So the many small vectors are formed like that. All the vectors, these are summated together and form the interventricular depolarization vector. This interventricular depolarization vector, it is the small vector. moves toward left to right side and down to upper side, है ना, from the down to upper side and the left to right side. It is the small vector and it represents septal activity. This vector or interventricular depolarization vector is the small, but it has the fast conduction velocity because of the presence of the Purkinje fibers. Because of the presence of the Purkinje fibers, first it has the fast conduction velocity. So the third electrical activity of the heart is the depolarization of the intraventricular septum. Now the wave of depolarization go through Purkinje fibers and causes depolarization of the whole of the ventricle. Depolarization of the whole of the ventricle. First, left ventricle depolarization, and then right ventricular depolarization occurs, and because of this wave of depolarization, small vectors are formed. All these vectors are formed in the left ventricular depolarization vector is formed. This vector, it is the very strong because of the strong musculature of the left side of the ventricle, and in the right ventricle also very small vectors are formed, and these all again are summated together and form the right ventricular depolarization vector. But this right ventricular depolarization vector is weak as compared to that of the left ventricular depolarization vector, because musculature is less as compared in the right ventricle, musculature is less as compared to that of the left ventricle. Okay, so right and left ventricular depolarization vectors are formed. So these right and left this left ventricular depolarization vector, it is toward the left and it is toward the towards the downward, and it is also the downward and toward the left. Now both right and left ventricular depolarization vector, they are summated together and form the one strong depolarization vector of the ventricle. And this strong depolarization vector of the ventricle, it is the strongest of all the vector, and it is from the moment is the upward toward the downward, and it is more toward the left side because of the left ventricular musculature. So this strong depolarization vector of ventricle, it is the downward and the more toward the left side. Now lastly the depolarization of the basal part of the ventricle occurs. Now the wave of depolarization move toward upward and toward the right side. It move upward and toward the right side. If it move upward or toward the right side, the vector produced, it is the upward and toward the right side. From the right side and the left side, both the vectors are the formed, and these vectors, these are the very small vector upward and toward the right side of vector is formed. So this is the depolarization of the basal part of the ventricle. Last part of the ventricle that is depolarized is the basal part. So there is the 5 events, electrical events occur in the heart. When we summarized it, it is the first electrical event as it is shown in the diagram that is drawn by me. It's not so good but manageable. First electrical event is the atrial depolarization. In the atrial depolarization, a small vector is formed. This small vector is formed because of the summation of all the small vectors, and they form the vector. It is the small vector and it is moving downward to the left side, and it is of the moderate velocity. Second electrical event is the AV node depolarization. It is very negligible, small negligible vector is formed, so it is not recorded in the ECG graph. Third electrical event is the intraventricular septal depolarization. Intraventricular septal depolarization, that is the small vector is formed moving upward to the right side, and it is the fast conducting vector because of presence of the Purkinje fibers. Fourth electrical event, it is the depolarization of the whole of the ventricle. Large vector is formed moving downward to left side, fast conducting vector. Fifth electrical event, basal part of ventricular depolarized. Small vector is formed moving upward to the right side. So this is all the electrical activity in the heart. Please go through this electrical activities in the heart very carefully, and then you are able to understand how the different waves of the waves in the electrocardiogram is produced. Now we know that ECG leads are required to record the electrocardiogram. Based on Enthovian assumption that the body is like an electrically homogeneous plate in which right and left shoulder and pubic region form the corner of equilateral triangle with the heart in its center, that which is called as the Enthovian triangle. The two active electrodes needed to be placed on that corners of this triangle. But practically it is not possible. So we are going to place the electrodes at the upper arm and the lower limbs. In the upper arm, right arm, left arm, lower limb. Okay. Now when we see the polarity of the leads which is connected to the electrocardiogram, in the right arm, in the lead 1, it consists of the two active electrodes connected to left arm and the right arm. Left arm electrode is connected to positive terminal, while the right arm electrode connected toward the negative terminal. So the current here, it is flow from the right arm to the left arm, because what, the current always flow toward the positive electrode. So right arm toward the positive arm. In the lead 2, there is a connection between the right arm and the left leg. In right arm again negative, and left leg it is the positive. So the current flow downward. It is current flow toward the downward and toward the left. While the lead 3, it is connected via the left arm, that is the positive terminal, and left leg, that is the positive terminal. Left arm, that is the negative terminal, and left leg, that is the positive terminal. So again the current flow in the direction of the positive electrode. So this is the placement of the leads. When we see all the electrical activities of the heart in the galvanometer, or when we connect the activities, electrical activities with the galvanometer, we get the different waves. So these are all the electrical events of the cardiac cycles. It is all the electrical events of the cardiac cycle. So our first electrical event is the atrial depolarization. Because of this atrial depolarization, first wave of the ECG is produced. It is directed upward, rounded, or it is the pointed. It shows the functional activity of the atrial muscle. So the P wave, it is the formed by the atrial depolarization. In the atrial depolarization, we saw the small vector is formed that is moving downward to left position. Downward to left, how we say, because in first lead, how it is, the right arm, in the right arm there is a negative electrode is attached, and toward the left lead there is the positive electrode is attached. As we know that the electric current, it moves from the negative toward the positive. So the atrial depolarization vector produce, it is moves from the upward toward the downward direction, and mainly toward the left side only. So the P wave, it is produced, it is the atrial depolarization, and because it is moving from the negative terminal of the ECG machine toward the positive terminal of the ECG machine, it show the upward deflection. Because the wave is not so strong, the vector which is formed is not so strong, so it show the rounded rounded shape. Okay, so P wave atrial depolarization, and this show the activity of the atrial muscle. Now the second electrical event is the AV nodal depolarization. Now the AV nodal depolarization, it is very low. It's very low, so, or the vector produced, it is the negligible or very small vector is the produced. During this time only the atria contract completely, and the ventricular contraction starts. So during this time no activity occurs. So when no activity occurs, so it is shown by the straight line. It is shown by the straight line because the vector which is formed is the very small. It is not recordable. So only one straight line is there. So we said that during this stage the heart is in the silent stage. So the plain line is there. Third electrical event, interventricular septal depolarization. In the interventricular septal depolarization, we saw that the small vector is formed, and when this small vector is formed, it is moving upward to the right side. Why it is moving upward toward the left side, the right side? Because the left ventricular musculature, it stimulates the interventricular septum. When it stimulates the interventricular septum, the vector formed, it is in the direction of the upward or toward the right side, and the vector formed, it is the fast conduction vector. Now the direction is from the upward to the right side, and our electrode we placed at the right arm, it is the negative, and the left foot it is the positive. So the our impulses, it moves from the upward to the right side. So it is the negative direction, or it is opposite direction of the current, it is the flow. So that's why the deflection produced, it is the negative or the downward deflection, because the current, it is moving against the electrode, or the current flow in the reverse direction of the electrode. Okay, generally the current flows from the negative terminal toward the positive terminal, and so negative terminal toward the positive terminal, that means downward direction. But interventricular septum depolarization vector, it moves from the upward toward the right side. So when it is moving upward toward the left side, it means in the reverse direction of the current flow. So it is the downward deflection and moving toward the right side. It is the fast conduction vector. Why it is the first conduction vector? Because the Purkinje's fibers are there, they help to move the impulses. So depolarization of basal part of the intraventricular septum. Don't mug all these things, only you have to understood properly what is that. First read the electrical events, how the vector is formed, and then connect these electrical events with that of the galvanometer or the ECG machine, and then see in which direction the vectors are formed. Is it going toward the direction of the current flow, or it is going opposite to that of the current flow? Understood? Now the fourth electrical event, that is the very important event. It is the depolarization of the major part of the ventricle. So depolarization of the apical portion of interventricular septum or apical portion of the ventricular muscles led to the formation of the R wave. And this R wave, it is the longest or very strong wave. Why it is a strong wave? Because large vector it is the formed, and it is the depolarization of the major part of the ventricle. All the part of the ventricle, it undergo depolarization. When it undergo depolarization, the vector which is formed, it moves downward and toward the left side. It moves downward and toward the left side. When it is moving downward and toward the left side, that it means it is moving in the direction of the current. So it moving in the direction of the placement of the electrode. That's why the R wave, it is the positive deflection, and it is, as it is the strongest vector or the large vector, the amplitude of the R wave, it is the more, it is the greatest as compared to the other vector. Now the fifth electrical event, depolarization of the basal part of the ventricle. Last part of the ventricle that is depolarized is the basal part only. We saw that small vectors are formed, and it moves upward and toward the right side. It moves upward and toward the right side. From both the corners of the ventricle, the vectors are arises and it moves upward and toward the right side. That means it is moving opposite to that of the direction of the current. So it is not moving from the negative toward the positive direction, but it is moving from the positive to negative direction. So it is the downward deflection is there. So the S wave is the downward deflection. P, silent heart, Q, R, S. After the S, the repolarization of the atria, that is the hidden by the depolarization of the ventricles. So the straight line is obtained. There is no activity of the heart during this point. After that, repolarization of the ventricle starts. In the repolarization of the ventricle, the T waves is produced. Repolarization of the ventricle, that is they form the small vector, and it is in the opposite direction of that of the depolarization. So this is how all the waves is formed in the heart when we record the electrocardiogram. When we summarized all the things, when we see all the electrical events, first it starts from the atrial depolarization. When atrial depolarization occurs, P wave is formed. And second is the isoelectric line is formed because of the stimulation of the AV node. At this time, heart is in the silent stage. Third electrical event, depolarization of basal part of interventricular septum. It gives rise to the negative Q wave. The Q wave, it is the small wave and it is the downward direction. Fourth electrical events of the heart is the repolarization of the apical portion of intraventricular septum and the apical portion of the ventricular muscle, mean the depolarization of the whole part of the ventricle. Now the depolarization of the whole part of the ventricle occurs. A big vector, large and the strong vector is the form that gave rise to the R wave of the electrocardiogram. The magnitude and direction of the R wave is very strong. That's why the R wave, it is the upward deflection. After that, there is the S wave is produced. S wave is produced because of the depolarization of the basal part of ventricular muscle near the atrioventricular rings. This is also the negative wave and it is the small wave. After the S wave, again the heart goes into the silent stage. After that, there occur the repolarization of the ventricular muscle. The repolarization, it is in the opposite direction to that of the depolarization. And it led to the formation of the P waves. Again there occur the depolarization followed by repolarization, and this cycles goes on. So it shows the electrical events of all the electrical events of the cardiac cycle. Now when we see the segments or the intervals. Segment is nothing but it is a straight line connecting two waves. Segment is only the straight line. Don't forget that. Segment is a straight line. While interval, it comprises at least one wave plus the connecting straight line. In the interval, one wave is there and one straight line is there. So don't get confused with the segments and the interval. Segment, it is the straight line connecting the two waves. Interval comprises at least one wave plus the connecting straight line. Now PR interval. There are the many intervals and the segments are present. First is the PR interval, QRS complex, RR interval, QT interval. While the segments are the ST segment, PR interval. PR interval, it is of the 0.20 second less than one large box. The PR interval, it is the distance from the start of the P wave up to the start of the R wave. So it is the PR interval and it is of the 0.20 second, less than one box, less than one large box. The time from the start of P wave to the start of QRS complex. It shows the atrial conduction plus AV node conduction plus bundle of his conduction. If PR interval is too long, it means conduction in the AV node is depressed, first degree heart block, which we will discuss in subsequent lectures. If PR interval is too short, it indicates the accessory pathway of fast conducting tissue is bypassing the AV node. QRS complex, start of Q waves and the end of the S waves. It represents the electrical activity of ventricles, causes depolarization of the ventricular musculature. Q wave, it is because of depolarization of interventricular septum. R wave due to the depolarization of the whole mass of the ventricle. S wave due to the depolarization of the basal part of ventricle. So the QRS complex, it shows the electrical activity of the ventricle. Clinical significance, bundle branch block, QRS is prolonged or deformed. Hyperkalemia, QRS is prolonged. RR interval, it is the interval between the two consecutive R waves. Normal duration of RR interval is 0.8 seconds. Measurement of the heart rate interval help to calculate heart rate variability. QT interval between the onset of the Q waves and the end of the T wave. Ventricular depolarization and the ventricular repolarization. It shows the activity of the ventricular depolarization and the ventricular repolarization. Duration is 0.4 to 0.42 seconds. Significance, prolonged QT interval shows the myocardial infarction, myocarditis. And when QT interval is shortened, QT symptoms and the hyperkalemia occur. Now the ST segment. The ST segment, it is the time interval between the end of S waves and the onset of the T wave. The point where ST segment starts is called the J point. Normal duration of ST segment is 0.08 second. 0.08 second. J point, it is coincides with the end of depolarization and the start of repolarization of ventricle. And this is present at the end of the QRS complex. Now the picture showing the depolarization and the repolarization. QRS, it is under the depolarization and the T wave is because of the repolarization. Now we come to the segments. Segments, it is a straight line connecting two waves. So ST segments are there, TP segments are there. ST segment, in time interval between the end of S waves and the onset of the T waves. The point where ST segment starts is called the J point. We already discussed what is the J point. Clinical significance, elevation of ST segment, myocardial infarction, left bundle branches. Depression of the ST segment, myocardial ischemia, posterior myocardial infarction. TP segments, period from the end of T waves to the beginning of the P waves of the normal cardiac cycle, the normal cardiac cycles. After interval and the segments, J point, it is the point at the end of S wave and the start of ST segment. It is the point of no electrical activity and it is important in assessing ST segment elevation and the depression. Now, very important point is that the depolarization of sinus node, AV node, his bundle and bundle branches is not marked on the normal ECG, as we already saw that of the AV node, because they do not contain sufficient cell to produce a voltage that can be measured on the skin of the body. That's why during the activation of this node, there is the silent period of the heart is there. So sinus node, start of the AV nodes, his bundle, Purkinje fiber. So we are getting the different point when we are getting the waves. Now his bundle electrogram. The electrical event in AV node, bundle of his Purkinje systems are frequently studied with a catheter containing an electrode at its tip that is passed through a vein to the right side of the heart and manipulated into position close to the tricuspid valve. It normally shows deflection when the AV node is activated and H is spiked during transmission through his bundle and V deflection during the ventricular depolarization. Now we are going to discuss the electrical axis of the leads. Hypothetical lines which joins poles of lead which measure electrical forces. Cardiac vector or cardiac axis, since the classical limblets 1, 2, 3 are records of the potential difference between the 2 points. Therefore, deflection in each lead at any moment indicate the magnitude and direction of the axis. Direction in the axis of the electromagnetic force generated in the heart. This is called the cardiac axis or the vector. When we do the vectorial analysis, a wave of depolarization traveling toward a positive electrode results in positive deflection in the ECG test, and then traveling away from the positive electrode results in negative deflection that we already discussed. Wave of repolarization travel in the opposite direction. When we see the axis of standard bipolar and unipolar limblets, so lead 1 electrode are placed at the right and left arm in the horizontal direction with positive electrode toward the left side. Axis of lead 1 is the 0 degree. In lead 2 electrode are placed at the right arm and the left foot, so it is making the angle of the 60 degree. When we consider the heart as the center as the 0, then it is the axis of lead 2 is the 60 degree. When we see the axis of the lead 3, then lead 3 it is the place between the left atrium plus the left leg, it is the 120 degree. So axis of the lead 3 is the 120 degree. Direction of axis of each lead forms the hexagonal referral system or triaxial reference system. Electrical axis of the heart. The mean electrical axis is the direction of the large vector in the limblets. It correlates with the long axis of the heart. Normal mean electrical axis is about 55 degree and it is between the minus 30 degree to 110 degree. QRS complex has the largest vector. Simply the vector is drawn from negative toward the positive end. if the voltage vector of the heart muscle is in the same direction as the vector of the lead, then the wave will be the positive. If the voltage vector of the heart muscle is in opposite direction as the vector of the lead, then the wave will be positive. Voltage amplitude, positive or negative, it is directly related to mass of tissue undergoing depolarization or repolarization. Orientation of the voltage vector with respect to the lead axis or the vector. So this is the summary of cardiac electrical activity which we already discussed, how the vector is formed. Now the mean electrical axis. Of QRS complex is more useful and is determined from the two standard limb leads, as the Q and S waves negative values, R wave positive value. The Q and S waves are added algebraically to the R wave for each of the two leads. The result gives the magnitude and direction of QRS vector, that is positive or negative at each leads. Net potential and polarity of QRS complex are calculated in lead 1 and lead 3. For example, in lead 1, the algebraic sum of R is plus 13 and S wave is minus 5. So, lead 1 and lead 3 is equal to, so in lead 1, the algebraic sum of R and S wave is the plus 13 minus 5, so it is the 8 millivolt. In lead 2, when we see the R and S wave, it is the R is the plus 15 and S is minus 0. So it is plus 15 millivolt. So when we see the potential in lead 1 and lead 3, then mean QRS vector is equal to 15 mm. Then we draw one perpendicular at the lead 1 and lead 3. We are getting the potential of the second lead. So when we draw the one perpendicular through the first and the third lead, we are getting the electrical axis, that is the plus 60 degree, or it is near about the plus 50 or the plus 60 degree. So this is how we are going to calculate the axis. We will discuss this more during our practical time. This is only the example of that. We are going to discuss during the practical time when the college reopens. Thank you.